In this video, we'll learn how to predict the chemical structure of any compound for all the spectral data given. First, you need to calculate degree of unsaturation. Degree of unsaturation formula, it's a number of carbons over number of hydrogens over 2, number of halogens over 2, plus number of nitrogens over 2, plus 1. So it's 12 minus 16 over 2. We don't have any halogens or nitrogens, so plus 1. That gives 5. So the degree of unsaturation is 5, which means we have either 5 ring systems or 5 pi bond systems, or the number of pi bonds and rings is 5. From the molecular formula, we see 2 oxygens. But from the IR, we do not see any broad peak at around 3000 centimeter inverse. Any broad peak at 3000 centimeter inverse could be alcoholic OH or phenolic OH or carboxylic acid OH. So the absence of broad peak confirms we do not have any alcohol or phenol or carboxylic acid functional group. The peak at 1660 confirms there is a carbonyl functionality. Let's see what functional groups contains a carbonyl group. Aldehydes, which is C double bond O with hydrogens, and ketones, which is C double bond O with the other alkyl substitution, and ester, C double bond O, O and alkyl group, anhydride, C double bond O, O and C double bond O and R group, and also amides, C double bond O, NH2 and Sl chlorides, C double bond O with halogens. And also carboxylic acid, but I'm not writing down the carboxylic acid because we already confirmed there is no carboxylic acid functionality in the molecule. Now we can eliminate the functional group amide because we do not have any nitrogen in the molecular formula given. Also Sl chloride, since we do not have any halogens in the molecular formula given. Now if you observe the anhydride, for anhydrates we need to have 3 oxygens, but we only have 2 oxygens, so we can eliminate the anhydride. So we end up with possibility of having 3 functional groups, which is aldehyde, ketone and ester. Now we can further simplify this selection by using Proton Nmr. This is the Proton Nmr belongs to that compound. If we have any aldehyde molecule, we should see a peak that belongs to aldehyde hydrogen between 9.5 and 10. Since we do not see any peak between 9.5 and 10, there is no functionality of aldehyde in the molecule. Since we do not see any peak belongs to aldehyde hydrogen between 9.5 and 10, we can eliminate the aldehyde functionality. Now we left with only ketone and ester functional group. From Proton Nmr we have 4 signals, which means there are 4 sets of chemically different hydrogens in the structure. And among those hydrogens, if you look at these 2 peaks, the expanded version given here, the peaks are between 6.5 and 8. In Proton Nmr, the peaks between 6.5 and 8 are aromatic hydrogens, which means we have a benzene ring in the structure. Whenever you see the integrations as given here in Proton Nmr, you can measure the height of the integration in order to find out number of hydrogens for each peak. For that you need a ruler. Now I'm going to measure the distances here. So the first peak is 0.3 and second peak is 0.3. And this peak is 0.45. And this peak is 1.4-ish. Now if you see the ratios of the numbers, it's a 0.3 versus 0.3 and 0.45 to 1.4. Now divide everything with the least number, which is 0.3. If you divide all the numbers with 0.3, we end up with 1, 1, 1.5, and this is around 4.6-ish. Now multiply this with 2 to get the whole number. 2 times 1, 2 times 1, 1.5 is 3, 2 times 4.6 is 9.2-ish, so I'm taking 9-ish. Now if you count the number of hydrogens here, it's 2 plus 2, 4, 3, 7, and 9, 16. So from the molecular formula we have 16 hydrogens. So for each peak we have, the first peak has 2 hydrogens, second peak has 2 hydrogens, third peak has 3 hydrogens, and the fourth peak has 9 hydrogens. This is how you can find the number of hydrogens for each peak. So we calculated 2 hydrogens for this peak and 2 hydrogens for the second peak, which means there are 4 aromatic hydrogens. So the benzene ring must be disubstituted. Let's see the possibilities of disubstituted benzene ring. It could be 1,4 substituted, or it could be 1,3 substituted, or it could be 1,2 substituted. Let's see the case number 3. In this case, we have 4 aromatic hydrogens, but these 2 hydrogens are chemically different, and these 2 hydrogens are chemically different. So we should see more than 2 peaks in the aromatic for this case. So we can eliminate this possibility. Now if you see 1,3 substituted benzene ring, in this case we have 1, 2, 3, 4 chemically different hydrogens. In this case also we should see more than 2 peaks, so we can eliminate the possibility. In this case, these 2 hydrogens are chemically same because these 2 hydrogens are next to a substitution A, and they have hydrogens, and also the next connectivity is carbon with substitution B. So these 2 hydrogens are chemically same. In the same way, these 2 hydrogens are chemically same. So we have 2 sets, and which gives 2 peaks in the aromatic region. And also each hydrogen has 1 neighbor hydrogen, so each peak split into 2. So this kind of disubstituted benzene ring gives a peak something looks like this in the aromatic region. These peaks looks the same, so we have 1,4 disubstituted benzene ring. And also the peak between 2.5 to 4.5 belongs to a carbon attached to an oxygen or nitrogen. Since we do not have any nitrogen from the molecular formula, this belongs to a carbon attached to oxygen. Now let's look at the carbon C13 NMR spectrum. Here we see two kind of spectrums. One is proton decoupled, other one is depth spectrum. Depth spectrum helps to see primary, secondary, tertiary and quaternary carbons. So remember, we see only the chemically different carbons in the carbon NMR. The difference between proton decoupled and depth is the primary and tertiary peaks will stay same between proton decoupled and depth, but any secondary carbons peaks will be flipped upside down. And also we do not see the quaternary carbon peaks in the depth, which means if any peak present for quaternary carbon in proton decoupled will be missing in depth. Now if we compare proton decoupled and depth, the first peak is staying same between depth and proton decoupled, so it's not flipping upside down or it's not missing either this primary or tertiary. Now the second peak, we do not see that peak in the depth, which means this belongs to a quaternary carbon. Now the third peak is staying same, so which means this could be primary or tertiary. And also the peak this peak staying same, which means this is primary or tertiary, but we are missing this tiny peak in the depth, which means this is quaternary. But this peak staying same, which means this is primary or tertiary. Now if you look at these two tiny peaks, we do not see those peaks in the depth, which means these two are quaternary carbons. We confirm benzene ring and also we confirm a carbonyl. And we have aromatic carbons that gives 1, 2, these two carbons are chemically equivalent, so 3, and these two carbons are chemically equivalent, 4. So we should see 4 peaks in the carbon NMR for disubstituted benzene rings, and among those 4, 2 are quaternary carbons. In carbon NMR we are seeing 1, 2, 3, 4, and these two are quaternary carbons and these two are other carbons. So we left with one peak here around 210. So what kind of peak we'll see at 210? We see ketone carbonyl carbon at 210. So from the carbon NMR data we confirms we have a ketone carbonyl but not ester. So this is all the information we have so far. We have a carbonyl functional group we confirm from IR and C13 NMR, and we confirm a methoxy, and also we confirm a 1,4 disubstituted benzene ring from proton NMR and carbon NMR. So if we put all the information together, so far we solved the structure for C8 H7O2. But the molecular formula is C12 H16O2. So we have to assign structure more for 4 carbons and 9 hydrogens. So for this 9 hydrogens, we should have 3 CH3 groups, and also these 3 CH3 groups connected to a carbon with no hydrogens. Just like the way we confirm this as methoxy OCH3, because the 3 hydrogens is connected to atom with no hydrogens, because this is singlet. This is also singlet, which means those 3 CH3s, those 3 CH3 connected to a carbon with no hydrogens. So we confirm a group, something looks like this, CH3, CH3 and CH3. So for C4H9, we confirm the group Now let's try to put all the fragments together. We have a benzene ring 1,4 disubstituted, and we have a ketone, and we have a methoxy, and we have a tertiary methyl group, a tertiary butyl group. So the possible structures are this is the only possible structure, because we cannot connect methoxy group to the carbonyl, because we already confirmed we do not have any ester. So we have ketone and methoxy group. Now you need to assign all the peaks. Two, 3, 4, 5, 6, 7, and 8 for these 3 hydrogens, because they are chemically different, chemically same. So here, these 2 peaks belongs to 3 and 4. And the OCH3 is 1, so I'd say 1 here, and 3 CH3s, this is 8. And also for carbon NMR, this will be quaternary carbon, it's 7, and this is primary and methoxy carbon, and this peak belongs to 8. These 2 are 3 and 4, so the tiny ones 2 are 2 and 5, and this tiny peak belongs to here is carbon 6. Now you guys can assign IR. It's already here, C double bond O and C double bond C, and here the tiny peak here, aromatic hydrogens, and this is here sp3 carbon hydrogens. So this is how you assign the spectra.